right, good afternoon again. So this is our third lecture in our new physics class. King Henry died by drinking chocolate milk. What a shame. He actually didn't. King Henry VIII did not die by drinking chocolate milk. Of course, he certainly could have, I guess. When was cocoa first discovered and refined? And I guess the Spanish would have done that. Of course, the Incas and the Aztecs probably, got to give credit for them. But I think that was the Spanish that actually started making it into the drink that we know as hot chocolate. So anyway, the SI system of measurement. This is not about chocolate milk. It's not about King Henry at all. This is about a method of conversion. This is a good way to memorize the different metric prefixes. So let's get into it. Okay, so we're going to introduce the SI, System International, previously known as the metric system of measure, the common prefixes that we're going to encounter in X-ray science. Compute common conversions between SI and Bridges system. I'm not sure if I actually do that. Maybe I do. Centimeters to inches and kilograms to pounds are the most common conversions you would need as a healthcare practitioner. So if those are in there, I will definitely mention those. 2.54 centimeters to an inch, 2.2 kilograms to a pound, if they don't come up again. So I'm not sure if I chopped those or not. So order of operations for algebra. We may be doing that, may not be doing that. So we're stacking pieces of information. We've already covered algebra review. That was week 1, and scientific notation. Okay, and so the metric system scales magnitudes by powers of 10, very much like scientific notation does. And so it's if you're using scientific notation in combination with metric units, then scaling is easy. You just subtract exponent powers to the power of 10 or add exponent powers to the power of 10. You don't have to change the value at all, and you can change kilometers to meters, or meters to millimeters, or millimeters to meters. If the number is already expressed in the power of 10, the metric prefix represents its own power 10, like kilo represents 10 to the third. So it's the same as multiplying by 10 to the third, or dividing by 10 to the third in some cases. So we'll get into that. We'll get into the King Henry method. It's called the ladder method. We call it King Henry died by, the way that I learned it was King Henry doesn't usually for base units, unit starts with AU, but I guess the more modern one, and I found a hysterical song that's linked at the end of this. Won't be able to play it on the recorded lecture, but the link does work. So if you get the master original version of this PowerPoint, you can click on that. I will be playing the song when I give the live lecture to my physics students here. Probably right around, I think this is going to be week 3, so this is going to be right at the end of January. We're going to do this. Rules of scientific notation, special radiologic units of measure. We're definitely covering those. I don't know if I covered order of operations again or not. That might be a typo from a previous PowerPoint. So let's get into it. All right. So understanding radiologic physics and understanding all science. Okay, we enhance our understanding, and this is a good example of enhancement of understanding. Okay, there's 2 scenarios here in this. All right, so quantifying, that is measuring the amount of something involved in our situation, gives us more detail than so an objective measurement gives us a more specific understanding of what's going on. And this applies to healthcare, but it also applies to baking apple pies, apparently. So a recipe for apple pie calls for 6 apples. Must be a deep dish then. Yum. Okay. So in scenario A, Jim has some apples. In scenario B, Jim has 7 apples. In which of those scenarios are you absolutely certain that Jim has enough apples to make a pie? You see, it's scenario B. Why? Because you know that 7 is bigger than 6. You understand that that's a measurement. Okay? He has counted the number of apples, and the number of apples is 7. The recipe calls for 6. He has more than enough apples. He'll have 1 apple left over. Okay? What are the units of measure in this example? It's apples. That's right. It's apples. Okay? And so units of measure for physics are more standardized. We're talking about there's parameters like distance or length, and then there's units of measure, meters. Okay? And so there's a fundamental difference between, right, meters and the parameter that it's measuring. Those are 2 different things. Okay? And that will come up again in X-ray science as one of my pet peeves. Okay? Spatial resolution is not measured in line pairs per millimeter. Spatial frequency is. Spatial resolution is the subjective version of spatial frequency. Spatial resolution is good or poor or better or worse. It's a subjective. Okay? Spatial frequency is the enrichment of understanding by quantification. It's the objective measure. Okay? Spatial frequency has a units of measure of line pairs per millimeter. Okay? Some of my fellow colleagues in the teaching arts of radiologic science that have written questions for publishers and textbooks have forgotten the difference between subjective descriptors, spatial resolution, and objective parameters, spatial frequency, which has a units of measure, line pairs per millimeter, and it drives me crazy. What is the spatial resolution in line pairs per millimeter? Well, your sentence doesn't make any sense. I have to answer your question because this is on the registry exam, but you don't know what you're talking about. Speaking of revealing some ignorance, all right, so NASA wants to build a Mars orbiter, but we don't want to do the work. We want to farm out the work to our buddies that work over at Lockheed Martin and JPL, Jet Propulsion Laboratories. Okay. Now, most of the time, both of these groups of individuals, they're physicist engineers. They're amazing. They're astrophysicist engineers. Both the Lockheed Martin boys and the JPL boys. And it actually is the Lockheed Martin engineers. And I said boys, could be some girls too. Okay. Lockheed Martin engineers are the ones that mess this up. Okay. And so NASA tells Lockheed Martin, hey, you guys design the instrumentation and the software design a circuit board that can get information from sensors on the orbiter and calculate its velocity and its GPS trajectory on Mars, where there is no GPS tracking, there is no GPS metric. We need this Mars orbiter, the computer guidance system, to be aware of its altitude over the Mars surface and its velocity. And we need you to develop sensors and a software that can report these measurements from the sensors on a circuit board and send that information, that data, to the guidance circuit board, which is being designed by JPL, so that the thrusters that maintain the orbit and correct course for the orbiter, for this little Mars satellite, so it stays in orbit. Okay. Well, you can see I'm very long-winded. If you've already read this, you figured out what happened. Okay. The sensors and the Lockheed Martin software circuit board took measurements in the imperial system, that is, feet per second for velocity, or miles per hour, but I think it was feet per second. And the altitude was measured in either miles or feet. Okay? And so the numbers are, the magnitudes are based on feet and feet per second. Okay? JPL writes their software for their guidance thrusters and how long do you run this, the left quadrant thruster versus the right quadrant thruster versus the center thruster, so on and so forth, which you burst fire the thruster and it, by Newton's third law of motion, it repositions the satellite and adjusts its altitude or adjusts its heading so that it doesn't turn into a piece of artillery. It doesn't start plummeting. Okay. JPL assumed that the input measurements from the sensors being written by Lockheed would be in the metric system and base their calculations on metric calculations. So Lockheed Martin was using feet per second. JPL was assuming that that was meters per second. Lockheed Martin was reporting the altitude in either miles or feet. JPL assumed that that was meters. The Mars satellite orbiter promptly crashed as soon as it tried to maintain a stable. It was deployed from the rocket pod, the last stage of the booster, started taking in sensor data, applying that, and trying to course correct, and promptly crashed to the surface of Mars. This project cost the American taxpayers $125 million to basically, within the first 5 seconds of deployment, burst into a ball of flame and hurtle down toward the surface of Mars and crash into the desert. Now, the funny thing is when they figured out what the hell went wrong, JPL rewrote their software in a circuit board that they had in California and added in conversions to the metric system before applying that. Okay. And by doing so was able to model the trajectory of plummet, like the arc of the fall of the satellite with a computer system on Earth, and be able to, they computer modeled the crash arc, okay, because they just lost communication with it almost instantaneously, and like everyone's scratching what the hell happened, right? And then about 2 months later or so, I don't know, I'm making that up, 2 months, 2 weeks later, we figured out that this happened probably in a conference call with Lockheed Martin. So they plotted the trajectory of plummet and applied Newton's laws of motion to the formulas with the adjusted data, plotted a parabolic arc, right, and was able to pinpoint, they said it's going to be in this location, right? And so the next time the telescope was pointing at Mars or could see Mars in the night sky, I'm not sure what side they basically called up some telescopes and said, hey, we need you to look at this specific quadrant, right? They have Mars, the surface of Mars mapped out so they can say, like, look at the middle of Q47 or the upper right hand corner of Q47 or whatever, right? And see if you see a like an impact crater or carbon scarring or something resembling a crash. And sure enough, within 2 meters of where they indicated that the satellite would crash, so Newton wins again. Um, Within 2 meters of where the computer model said the satellite crash impact zone would be, that's where Earth-based telescopes located the crash site, and they were able to confirm the error, thanks to Isaac Newton and some, some gnashing. I'm sure there was some gnashing of teeth, and probably some people got fired over that. They totally deserve that. Come on, we're proper scientists here. The metric system is the only functional system we should be using. All right. The metric system is fundamentally better than the imperial, like feet and inches and pounds, and it's all arbitrary. Okay. You know why we call it a foot? Because some long dead king in right around the time, because England used to be a colony of the Roman Empire, and then there were native Celts there, and then the Vikings invaded, and then the Britons, which were actually descendants of the native Celts, and then there were the Scots, and basically there was a fight for control, right? Somewhere around that time, right after the reunification of England as an official country, somewhere along that line, one of the kings of the lords, I think it was a king, said we need a measurement, and we're going to use my foot for a system of measure. So the length of my foot is a unit of measure now. Okay, so it was literally a king's foot. Whose foot? Which king? We don't know. Okay, but that's why 12 inches is a foot, is because that was the crude system of measure. They said, well, the king's foot is the fundamental unit of length. So, and I don't know how the inch came about as a 12th of the king's foot, but the king's foot, that was some big feet, 12-inch long feet. Anyway, well, it's not consistent, okay, and it's not standard. It's partially standardized, but it doesn't make any sense, and you got all these screwy numbers. How many feet in a mile? 5280. Okay, five tomatoes. That's how I remember it. 5280. 502,080 feet in a mile. Okay. Do you want to do conversions with the number 5,280? Or do you want to do it with 10? Divide by 10, or multiply by 100, or divide by 1,000? Which one seems simpler and easier to master? Yeah. So thank you to the French Revolution. That's where we got these things. Fundamental quantities of mass, length, and time predate both of these systems of measure. Mass is basically the amount of stuff, the amount of matter you have. Length, of course, is, we live in what we perceive as a three-dimensional realm. There's new theories about that, but for base observations and the classic Newtonian system, there are lengths and widths and heights. And reality as we know it has 3 dimensions and time. So you can go that way, or you can turn 90 degrees and go this way, or you can go up, or you can go down. Okay, and each one of those, you can draw a line in each of those 3 directions. You can have 2 points on that line, and there's a distance between those 2 points, and that's what we mean by length. Okay, so length can be in the on the x-axis, on the y-axis, or on the z-axis. And then time, well, I've got slides coming up on that, so don't want to spoil that. Okay. Derived quantities, well, after we started thinking about things, it became useful to create new units of measure that were combinations of certain other units of measure, like length. So volume is a good example of that. Volume is the space that an object occupies. And if it's a rectangular prism, then you measure the length, the width, and the height, and you multiply those numbers together, and you get the volume. Okay. If you want to measure how fast something is going, just the magnitude of that's called velocity. The magnitude, or just the magnitude, is called the speed. The magnitude in the direction is called the velocity. Okay. Both speed and velocity are measured in meters per second, which is length divided by time. How long does it take to get from point A to point B is the idea of velocity or speed. Okay. Acceleration is the change in velocity over time, right? So if you go from 5 meters per second to 10 meters per second, and it takes you 1 second to make that change, then you have accelerated at 5 meters per second squared. Okay. Force came about. I'm not sure if it was Isaac Newton that first proposed force, or if it was some other person and he just quantified force. But force is mass times acceleration. Okay. Force is invisible. We can't measure it. We can only derive it we can measure length and time, and then we can calculate velocity and acceleration. And then if we know the mass, we can calculate the force. But we can't directly observe the magnitude of the force. We can only observe velocities and accelerations. Okay. The human eyeball is very good at detecting acceleration. Hey, that thing's standing still. Oh, look, now it's moving. Acceleration. Okay. Remember, things that we say are standing still, that's got a velocity of 0. Okay. So, and then momentum, which we will avoid because momentum gets tricky when you change it into electromagnetic waves. But momentum is explored if you were taking theoretical physics, we would talk at length about momentum. And then if you were taking classical mechanics or college physics 1, you would talk about work and power. We are going to mention power when we get to electricity. And all of those are combinations of the fundamental quantities and then combining some derived quantities. So work, for example, is force times distance. And then force, you remember, was acceleration times mass. And then acceleration was length divided by time twice. Okay. And so work is really, let's see, that's mass times length divided by time twice and times length again. Wow. Okay. And then when we get to the discovery of radiation, we had to create special units of measure for radiation quantities. Okay. Like dose equivalent, exposure, and radioactivity. Okay, so metric prefixes these are Latin roots that mean they have been assigned the meaning of certain powers of 10. So kilo is in bold. We are going to encounter, I think, once or twice mega electron volts for one of the equations. But kilovolts means 10 to the third volts, or it's the same as saying 1,000 volts. So if you have 10,000 volts, you have 10 kilovolts. Okay. So it's a shorthand basically to make the numbers, again, just like scientific notation, let's make the numbers smaller. So we don't want to say 10,000 meters, right? Because you have a hard time picturing that, right? Because the quantity is so big. But if you say 10 kilometers, oh, yeah, well, yeah, I can wrap my head around that. That's, you know, and, of course, we're used to miles. I don't know off the top of my head the conversion between miles and kilometers. I'm pretty sure the kilometer is shorter though, but I think it's really close to like 2/3 of a mile. So, but we are going to use kilovolts extensively. It's one of the fundamental settings for technique is kilovolts. So, right. I'm not going to play the video during the recorded lecture, but this is Doc Brown from Back to the Future 1, freaking out about gigawatts, which from the previous slide, I think it's 1 billion watts or 10 billion watts or something like that. So, and then we get into some of the more useful stuff: hecto, deca, deci, centi, milli. Base units is in between deca and deci. Okay. So just meters is in between a decameter, which is 10 meters, and a decimeter, which is 1/10 of a meter. And then centimeters, that's probably one of the more familiar to you. You've probably seen centimeter measurements, maybe millimeter measurements. Okay. And then we do have to include micro and nano because nanometers is the measurements of wavelengths of X-ray photons are typically in nanometers scale. Okay. And then picometer, in between nanometers and picometers is the angstrom, which is about the size, 1 angstrom is about the size of the diameter of an atom. Okay. All right. Metric conversion. This is where we get back to King Henry. Okay. Which that is a cartoonish version, and he is not rotund enough to be the real King Henry. So, but King Henry died by drinking chocolate milk. I do like this one better because it was really hard to. The version that I learned, King Henry died, or King Henry doesn't usually drink chocolate milk, or King Henry died unexpectedly. Well, base unit. So when you hear usually, that stands for unit, meaning base unit, like meter, kilogram, or liter for volume. Let's see, time, seconds. So we are gonna have milliseconds that we have to deal with, and you will have to convert though because mass is expressed as a product of milliamperes and seconds. But when the exposure time is in milliseconds, we're going to have to convert back to seconds to properly calculate the mass, or the magnitude of our mass will be off by about a factor of 1,000. Okay. All right. So fundamental quantities, mass. Mass is just the quantity of matter. Okay. So the Earth, yeah, that's a big boy. Yeah. Roughly 6 times 10 to the 24th kilograms. By comparison, I am a scant 110. That's my fighting weight. 110 kilograms in this corner, Mr. Tilton. Yeah, watch out. I've got a hell of a reach, y'all. The moon weighs about 1/6, roughly, the size of the Earth. Okay. Or in powers of 10, that's about a difference in magnitude of about, oh, not 1/6. Where did I get 1/6 from? It's about 100 times less massive than the Earth. Oh, it's the gravitational field is 1/6. That's what it is. Yeah. Okay. Can of Coke. Can of Coke is 4/10 of a kilogram, right? And so, but when you drink it, you gain 2 pounds if it's high fructose corn syrup Coke. So, magic. That doesn't make any sense, but yet it happens. Okay. I wonder how much a slice of cake, because a slice of cake is not 2 pounds. You gain 2 pounds by eating the slice of cake, but I don't think a slice of cake is 2 pounds. You couldn't eat 2 pounds of cake in one sitting. Yes, that is a challenge. Okay. Carbon atom, 2 times 10 to the minus 20 kilograms of mass. Okay, so if you look at those numbers and look at magnitudes, I'm 1.1 times 10 to the second in scientific notation. Okay, so how big is a carbon atom? Well, in comparison to me, a carbon atom is as big to me as I am to the Earth. It's the same scale of magnitude. Okay. The Earth is a magnitude of 10 to the 24th. I'm a magnitude of 10 to the second. That's a difference of 10 to the 22. Okay? I am 10 to the second. A carbon atom is 10 to the minus 20. That's a difference of 10 to the 22. So yeah, carbon atom, if you picture me relative to the size of the Earth, that's how big a carbon atom is relative to the size of me. Okay? And so you can see how small both of those are. Okay. Or large, small and large, subjective. That's why we have these numbers. Okay. So the base unit of mass is the kilogram. It was the gram, but then they found out the gram, unless you're measuring out drugs, the gram is way too small to be functional. Like if you're talking about the weight of people, kilograms is much more useful than grams. Okay. So a kilogram is 1,000 grams. Kilograms is more useful as far as human-sized scales. Kilograms is much more practical and useful to us than grams are. Grams are useful in the chemistry laboratory, or when you're cooking meth. Grams are you're going to want a gram scale. So you can make the Primo 99% pure blue ice. You're going to want a gram scale for that, okay? But if you're not doing chemistry, either legitimate chemistry or the non-legitimate kind, careful, okay? You're not going to be using grams. Grams is too small of a unit of measure for most stuff. Okay. Now, what is the gram? How much quantity of stuff is that? Okay, so a cubic centimeter of water at exactly 4 degrees Celsius weighs 1 gram. So that's the standard for determining what a gram is. Okay, when we adopted the kilogram, they have a chunk of, I'm not sure if it's iron or it's probably something that doesn't rust as well as iron does. So it's a metal. It's probably a rare metal that is not corrosive. It doesn't react with oxygen. I forget what they made. But France actually has the original kilogram under glass in a vacuum. Okay. Every other kilogram standard in the world is based off of this chunk of metal that they have in a museum in France. They hold it. They basically have a building set aside for the SI standards, right? And the kilogram, the original kilogram, is in this building in France. Okay. Now there was a controversy, but I don't want to. Basically, the kilogram in France started changing its weight or its mass. It started shedding mass, okay, or its mass was fluctuating, okay. This was, I think it was back either in the 2000s or the 1990s. If you're curious about it, you can look it up and read about it. But there was a crisis with a kilogram, okay. But 1 kilogram, there you go. There's your conversion to English units. 1 kilogram, 2.2 pounds. Occasionally, like when we do cross-table lumbar spines, what we used to say is a good mass was half of the patient's body weight. Now in the digital age, I would say probably 1/4 the patient's body weight in pounds. Okay. The problem is in the hospitals, for administration of drugs, they're going to chart the patient's body weight in kilograms. Okay. And so you're going to need to know how to convert the patient's body weight to pounds in order to use that trick for setting technique. All right. Another fundamental unit of measure is distance or length. Okay. And so distance is a measurement of space in a three-dimensional environment. The SID for a chest x-ray is 1.8 meters, roughly. Okay. So 50 kilometers from this hospital to my house, okay, approximately, okay. And so if we adopt SID for a chest x-ray as a unit of measure, you could do 27,778 chest x-rays back to back between Nashville General Hospital and my house. Okay. And I just ran with that joke. Distance between Nashville and Menlo Park, where Edison's lab is now a museum, 1,407 kilometers, which is 781,667 chest x-rays lined up back to back. Earth to the moon, you get the point. Now the distances are getting ridiculous. Okay. Distance light travels in 1 second. So that X-ray photon, does it arrive at the image receptor instantaneously? Yes. Look at how fast the X-ray photon travels. You can do, if that same X-ray photon was traveling for 1 second, it could travel the distance of 1.6 times 10 to the 8th SIDs in a second. That is crazy fast. Okay. And then another handy conversion. Now I think we said on the registry we're going to the metric system, but I think that we were slow to adopt changing SIDs to metric units. So they still say 40 inches, but they give, as far as I know, they give 100 centimeters in parentheses. Okay, so they haven't fully converted to, but I think that change will be coming soon, where we're going to, hey, we're not going to say 40 inches anymore. We're going to say 100 centimeters or 180 centimeters instead of 72 inches. But for right now, they give both units when they're talking about SIDs. Okay. Or they just do 40 and 72. Okay. 1 inch is 2.54 centimeters. So again, if you're working with a non-conventional SID and you want to do a technique conversion, and you want to do it in centimeters, you can convert from inches to centimeters by setting up a proportion with 1 inch, 1 over 2.54 is equal to 40 over X, and then you'll solve for X, and I think I did that on a previous one. So, all right, fundamental quantities of time, right? So yeah, the illustration, I'm not going to do that in the recording, but Mr. Shepard, for those of you watching from other programs, is my program director, and he's about 10 years older than me, so anytime I can throw an age joke in, I'm going to do so. So please enjoy my age joke here. That actually is a artistic representation of King Nebuchadnezzar from Babylon. So that's at least historic, but I do not think that that's Craig Shepard in the crowd. So Babylon, at least I don't, yeah, that's supposed to be a joke. He might actually be there. I don't know. I mean, we'll have to ask him. Babylonians. So the first, the zodiac actually is the constellations of the zodiac is the first way, and it might have been the Sumerians, We don't know. We don't have a lot of the Babylonians basically replaced the Sumerians. That's a nice polite way to put it. Conquered is another way to put it. Um, so the Babylonians might have developed the zodiac themselves, or it might have been developed by the Sumerians that were basically occupying the same lands before the Babylonian civilization spawned and developed, on top of the Sumerians, conquering, right? So we don't know if the Babylonians came up with it themselves or if they stole it from the Sumerians when they conquered them. So, but it was the zodiac. They noticed that there were groups of stars. They didn't have a lot to do. They didn't have the internet. They didn't have video games. They didn't have cable TV. So people would go out at night and watch the stars go by, right? They would lay out in the desert or lay out, next to the river and, just stare up into the sky. And they started telling, certain stars were clustered into shapes. One of them looked like a crab. Another one looked like a pair of fish on a stringer, right? So on and so forth. So they gave names to these: Gemini, Cancer, Scorpio, those type of things. That's where the zodiac came from. But they counted that there were 12 of them on the average sky, sometimes more, sometimes less, but on average, about 12 of them would pass. And then the sun would come back up again, and then you couldn't see the stars. Okay? And so they divided a day into 24 sections. Okay? Because there were 12 constellations that passed on the average nighttime, so that they reasoned that there were also 12 sections to the daytime. And that's where we got the concept of an hour from, was 12 sets of constellations would pass while we were watching stars all night. Okay? And then they had this fetish with the number 60, and it was reasoned later by mathematicians is 60 is great as far as dividing into subsets. You can divide 60 by the first 6 whole numbers, 1 through 6. 60 is divisible by each of those and turns into another whole number. So, and then it's also divisible by 10, 12, 15, 20, 30. So you could partition it, right? So the hour became partitioned into minutes, and then the minutes became partitioned into seconds or second minutes. Okay? And minute just a minute section of an hour. Okay? And we like the convention of base 60 because we can have quarter hours, we can have tenths of an hour, we can have half hours, so on and so forth. And so 60, the mathematical practicality of dividing an hour into 60 just works. And so we stuck with it. And so, the way we keep time now with hours, minutes, and seconds, years is a different thing. The Romans messed with the annual calendars significantly. But hours, minutes, and seconds, basically the way that we keep time now is the same way that the Babylonians and Sumerians, who invented the concept of time, keep time. Okay, we know now that the length of the day and the length of the year are really based on the rotation of the Earth and the revolution of the Earth around the sun. Okay, roughly. Okay, and then in order to better quantify time, cesium atoms have a frequency vibration. Okay, and we can use that too. So atomic clocks, the way that the length of time a second is determined is by an atomic clock with a vibrating cesium atom at its core. And we're measuring the vibrations coming off those cesium atoms. Okay. Um, yeah. So that's time for us. All right. Now, time is a human construct. We propose it's the weirdest of all the dimensions. It's linear and it moves forward but not reverse. Okay. Not yet, anyway. We haven't figured out how to move it in reverse yet. Well, not, there might be some government secret that we don't know about yet, but they haven't disclosed that to the public that we know how to move it in reverse yet. All right. Special radiologic quantities. When we discovered radiation, we had to quantify it because we're scientists. And so the Americans quantified it as the Roentgen Rad Rem, and the Curie and the SI system had to come up with a metric system, had to come up with separate units of measure because the Americans, they're still using miles and feet. They're so backwards, these Americans. Okay. The SI unit is the Coulomb per kilogram. For the rad, it's the gray. For the rem, it's the sievert. And for the Curie, it's the becquerel. Okay. Yes, that is another French name. Lots of French folks in early atomic theory, early science, and early radiation science. So, Madame Curie is, well, she's native to Poland. She was born in Poland, but she emigrated to France because the Polish didn't want to teach women at university. So, true story. All right. So, delving deeper, the gray is a measurement of air kerma, kinetic energy released in matter, the gray in air. Coulombs per kilogram is often used as well. Okay. The joule per kilogram is different than a coulomb per kilogram. Joule is a measurement of energy deposited into a mass of air, versus coulomb per kilogram is how many ionized charges are you creating in that same mass of air. So a slight difference between coulombs per kilogram, which is the standard SI unit of exposure, and grays in air, which is the energy released into, the energy deposited into the air to create those ionizations. So a slight nuance. Okay. Radiation absorbed dose. Okay. You will have this again in radiation protection and radiology, but repetition is the key to learning. So grays in tissue is the unit of measure for dose. Now we have photons depositing their energy in living tissue. Okay, so that is the fundamental difference between exposure and dose. Dose means, okay, now exposure is there's radiation present in the environment. Dose means that you've actually caught some of it, or some living thing has absorb some of that energy. Okay. It is also a joule per kilogram, but now that kilogram represents flesh, tissue. Okay. It is adjusted by multiplying by tissue weighting factor. We cannot measure grays in tissue directly. We measure grays in air, or estimate grays in air, and then we multiply by tissue weighting factor to get grays in tissue. Yes, you will have these lessons again in radiation protection radiobiology. The sievert is used to quantify occupational exposure, or dose equivalent. Okay. And again, exposure is being used incorrectly here. It is dose. Okay. Dose means radiation deposited into living tissue. Okay. Addresses biological effects of different types of ionizing radiation. So different types of radiation are more efficient at damaging tissue than others. And that's the real, the whole point of quantifying dose is estimating that tissue damage. Okay? So if we multiply grays in tissue by radiation weighting factors, then we get sieverts. Okay? Here's the problem. These are all metric units. Landauer and other dosimetry companies still report doses in millirems, which are the American units, not in sieverts. Okay. Becquerel is radioactivity. If you go into nuclear medicine, you will need to know about curies, millicuries, or millibecquerels. Okay. Becquerel couldn't be more intuitive. One disintegration or one radioactive decay event per second is 1 becquerel. Okay? It is a quantity of radioactivity. Okay? How much does the cesium glow? How much does the uranium glow? That's becquerels. Okay? Whereas dose is how likely is that to give, if you carry it around in your pocket, how likely is that going to give you cancer? Okay, that's the difference between radioactivity and dose. All right, electrical quantities, I tack these on here. We will revisit these when we jump into electricity. But charge is the quantity of electrons, basically for us. The strength of the local electric field, usually the property of a particle. And the free particles we're going to consider are free electrons. So when we're talking about charge in coulombs, we're talking about oodles and oodles of electrons. Okay, that leads to our understanding of current, amperes, which is the flow of charges in coulombs per second through an electric circuit. The push or pull on those electrons is the voltage. And then the resistance to that push or pull is ohms, and that's a property of the wire or the electrical device that we're using, that we're passing the electricity through. It is going to resist the flow of electrons. Naturally, you can't get rid of resistance. You can only reduce it. So that is our walk through the SI systems of measure. I think practically speaking, you should be familiar with the different types of measurements, the different units of measure, and those bolded prefixes. Not all the prefixes, but the bolded prefixes are most likely to show up in future concepts and future descriptions of X-ray science. Okay. The common conversions, the ones practically useful to you in the clinical setting, will be centimeters to inches and kilograms to pounds. Okay. And then, yeah, I'll play this live for you guys in physics. Maybe I'll link to it on the YouTube channel too. But yeah, that is a song about King Henry died by drinking chocolate milk, and it is well written. I think it's a ripoff of an actual rap song. So they changed the lyrics, but it flows. It's good. Yeah, I've seen some bad educational songs. This is a good one.